Good afternoon, everyone. My name is Richard O'Shea. I'm a postdoctoral researcher with the MARI Centre, which is an SFI Centre for Energy, Climate and Marine. And today I'm going to give a brief overview about the integration of renewable gas into future energy systems. A lot of it will have been covered by Ian and Xavier previously, so hopefully we'll clip along through it nicely. The motivations for MARI, as I outlined, are the energy transition, moving from fossil linear-based energy systems to circular renewable energy systems, climate action, the reduction of greenhouse gas emissions, and the blue economy, valorising and realising the resource associated with the ocean that surrounds this island. So looking at energy in Ireland, in 2018 this is total final energy consumption in Ireland, and kind of the big takeaway message is it's not just electricity. 80% of it is not electricity. A large chunk, totally dominated by fossil fuels, is the transport sector. An equally large chunk, dominated by fossil fuels, is the heating sector. So we are making incredible strides in decarbonising our electricity system, and that will play a role in heat and transport through the electrification of transport and heat. But there remains to be other areas within those sectors that will be difficult to decarbonise using renewable electricity. Taking a bit of a deeper look, the large blue wedge down here is transport, and that's totally dominated by oil. Looking at the residential and industrial areas, again, they're predominantly dominated by oil, gas and electricity. So we need to source more renewable energy in each of these sectors in Ireland. On a global scale, this is an example of where we get our renewable energy from. So in 2017, half of the global production of renewable energy came from modern bioenergy. So modern bioenergy would be liquid biofuels used in transportation, gaseous biofuels, either used in the production of heat or as a transport fuel, or the combustion of solid biomass in either combined heat power plants or district heating systems. Looking at the sectors where bioenergy would be used, it's predominantly in the production of heat and in transportation. Going forward, the International Energy Agency estimate that we need 145 exajoules of bioenergy, with a focus of 30 exajoules in transportation and about 2 to 3 exajoules of this from renewable gas. So what is renewable gas? Well, essentially it can be produced from any sort of biodegradable material, beach cast seaweed, animal slurry, grass silage, food waste, anything that can rot. You can put it into an anaerobic digester that was touched on previously, and it produces biogas, a combination of methane and CO2. You can remove the CO2 in an upgrading process, and then use the resulting biomethane anywhere you use natural gas today as a source of heat in an industrial, residential area, or as a transport fuel, predominantly in heavy goods vehicles. Moving into the future, you can also produce biogas from microalgae, pond scum. So essentially you can grow microalgae using the liquid effluent from a digester. You can also use some of the CO2 from your upgrading system to grow your microalgae. That microalgae can either be turned straight into biogas in a digester, or in a far more favourable situation, you can extract a high value product from the microalgae in a biorefinery, like omega-3 fatty acids. That provides the economic backbone of your system, and then your residues can be used in an anaerobic digester. You can also produce renewable gas from solid woody biomass, either through gasification or pyrolysis for the production of syngas. And that syngas can then be converted into biomethane, again to be used wherever you can use natural gas, provided it meets great quality specifications. And the final bit is actually renewable electricity. So I'll touch on this later, but you can convert electricity into hydrogen. Hydrogen can burn. You can use it in a fuel cell. However, in Ireland, we don't have a hydrogen infrastructure. We can't really move hydrogen through our gas network or certain portions of the gas network. What we can move is methane. So you can combine that hydrogen with carbon dioxide and produce renewable methane. That can again be used wherever you can use natural gas. So it's a way of converting potentially wasted renewable electricity from variable renewable generators into methane gas that can be used in areas where electricity finds it difficult to decarbonise. Again, one of the policy drivers for this is the Renewable Energy Directive, Mark II, and it sets out sustainability criteria for use of renewable gases or biofuels or bioenergy sources in transportation and heat. We didn't look at electricity in this study because in Ireland most of the electricity renewably will be sourced from wind. Looking at the hurdle you have to overcome in order to be classified as a renewable or sustainable fuel, it's about an 80% greenhouse gas saving for heat and a 65% greenhouse gas saving for transport, which means that it might be easier to use renewable gas as a renewable transport fuel rather than burning it in industry. It might be easier. Looking at why renewable gas can be sustainable and looking at how it can produce carbon negative fuels is predominantly around treating slurry, and Ian and Xavier hinted on this earlier. When you put slurry into a slurry tank, it produces methane. That methane is emitted to the atmosphere. Methane has a global warming potential 25 times that of CO2. So instead of storing your slurry in a slurry tank, if you put it into an anaerobic digester, some of it will leak out as methane. So if you leak 2% of the methane from a digester, and if you are combining that slurry with maize, you can still result in a carbon negative fuel at about minus 50 grams per megajoule. If you only use slurry, you're at minus 250 grams of CO2 per megajoule. And again, that is associated with the avoided methane emissions from not storing your slurry in a slurry pit. So looking at renewable gas, it can allow for decarbonisation across a number of sectors. Waste treatment, in terms of treating parkland wastes. It can also help to decarbonise agriculture itself. If you are an organic farmer, you can't use synthetic fertilisers. So you need to get a source of synthetic fertiliser or a source of renewable fertiliser so that your yield doesn't drop. The digestate from an anaerobic digester is better fertiliser than the slurry that goes into the digester. As well as that, you can also produce renewable energy so that if you've processing on site, it's still renewable. And as well as that, you can also use it to decarbonise big industry. Gosser is a brewery in Austria, and I think it meets about 40 to 50% of its thermal demand from the anaerobic digestion of byproducts in that brewery. Looking internationally, there is a growth in the amount of biogas upgrading that is taking place across the IEA Task 37 countries, predominantly in Germany, the UK, France and Sweden. So it's a growing area. An example of a biogas system would be one in Linköping in Sweden, which uses 7,000 tonnes per annum of pig slurry, along with 47,000 tonnes per annum of slaughter waste. Not nice things that you want lying around the place. It converts these wastes into biomethane, enough to power 65 buses, 10 waste collection lorries, 600 cars and a train. So it's essentially alchemy. You take something you don't want to see and don't want to smell and use it into something and turn it into something that is useful. Potential ways of producing biogas and the business models around them are interesting. One option is to go big. You have one big centralized plant. This is an example of a plant called Mabjörg, which processes 725,000 tonnes of feedstock a year, which is huge. If you build something this big, you're going to have issues with haulage on roads and traffic. So they decided to install pipelines to pipe slurry to the plant and pipe digestate away from the plant. So one potential model would be going big in a centralized manner. There are advantages and disadvantages. An alternative option would be decentralized production. Small farm-scale digesters or a number of farm-scale digesters producing biogas. This biogas can either be upgraded and hauled via the road, like Ian pointed out, or you can just pipe the biogas in low-pressure biogas pipelines to a centralized upgrading facility to produce biomethane. So there are a number of possible implementations. You can go big and centralized, or you can go small and decentralized. Which is best depends on what people classify as being best, whether it's community ownership, whether it's financial viability, or whether it's sustainability, or all three. Looking at Denmark again, currently there's about 10% renewable gas in the Danish grid, and they aim to have 72 petajoules of renewable gas by 2025. Reports state that they aim to reduce their natural gas consumption over time, and that would to the point where it's essentially 100% green. If you add power to gas to this number, you can get up to 100 petajoules, and I'll touch on power to gas in a moment. Looking into the future, something that hasn't kind of been touched on is that blue economy, the sea that surrounds this island. Seaweed is actually quite a good source of biogas. You can cultivate seaweed next to fish farms and integrated multi-trophic aquaculture systems. The seaweed acts as a biofilter, which removes the fertilizer released by the fish farms. If you harvest your seaweed, it depends what you want to use it for. If you want to use it for energy, you can harvest it at a point in the year where you optimize your energy yield. If you want to harvest your seaweed for a high value product like alginate, carrageenan or hydrocolloids, you can harvest it at a different time. If the seaweed is of high quality and you can use it in a biorefinery to make a high value product, use it in a biorefinery to make a high value product, because you can make more money that way. The residue, again, can be used in an anaerobic digester to produce biogas. Alternatively, if the seaweed is not of good quality, if there's issues with contamination in the water, you can ensoil the seaweed and make seaweed silage. We did this in our lab. And then run an anaerobic digester on that ensoiled seaweed throughout the year, because you can only harvest your seaweed once. This sounds futuristic, but it's actually happening in a place called Solrod in Denmark. They use beach cast seaweed, so seaweed that washes up on the beach, and they use byproducts from a carrageenan production facility along with some other food processing wastes to produce biogas. Microalgae can also be used. You can grow microalgae using the CO2 in the digestate from an anaerobic digester. You would need a source of heat. If you could burn some of the resulting biogas to heat that microalgae pond, fantastic. Again, that microalgae can be used to produce high value products, whether it's bio-based fats, bio-based proteins, or omega-3 fatty acids. So this is kind of getting into the idea of a circular economy where the output of one system is the input of another system. You can digest a residue, make fertilizer, grow microalgae, digest the residue, make fertilizer, grow microalgae. The final bit I'll talk about is power to gas. So this is the amount of electricity from renewable sources in Ireland in 2018 that was curtailed downwards. So you can have wind turbines that are producing power, but that power can't be used for a number of reasons. Either it can't be moved from where it's produced to where it's needed, and that's dubbed constraint, or you produce it when there's no load, and that would be curtailment. So essentially this power is wasted at the moment. One option is to build an interconnector to France and ship the power that way. Another option is to implement a power to gas system. You can produce hydrogen from this surplus renewable electricity, use the hydrogen directly if the infrastructure is there, or combine that hydrogen with CO2 and pump it into the gas grid or into methane, into compressed natural gas tanks, and use it wherever you would use methane. And again, this is happening in a place called Vertel in Germany. They have a food waste digester that's processing food waste. They get an electrolyzer. The electrolyzer is turned on by the grid operator. The carbon dioxide from the upgrading system and the hydrogen are combined in a catalytic methanation process to produce biomethane that is injected into the gas grid and is bought by the owners of 1,000 Audi natural gas vehicles. In an Irish context, this is a potential future. On the left-hand side of the graph, you can see the energy consumption in transportation. On the right-hand side of the graph, you can see the potential resource associated with different feedstocks in Ireland. If you focus in on the heavy goods vehicles, you can see that we could meet the entire demand of heavy goods transport in Ireland if we digest up to, let's say 80% of the slurry produced in the country. Now, realistically, that won't happen, but the scale of the resource that is available is significant. The same can be said for industrial energy consumption. If you look at the total energy consumption, gas, electricity, coal, peat, in the food processing sector, we can meet a significant portion of that through renewable gas if it fits. If a process can go to renewable electricity, let it go to renewable electricity. If a process can go to biomass, let it go to biomass. If there are processes that need natural gas, renewable gas is a viable alternative to it. So hopefully I haven't gone over time, and if you have any questions, I'll try and answer them during the panel.